I'm still thinking about this IMO solitaire problem, or at least I returned to thinking about it, and had just a small idea that made me think it was worth, because it's completely, the small idea has completely changed my perception of the problem, so I thought it might be worth just saying a little bit more. But again, I'm taking the attitude that I'm not going to push through the pain barrier on video anymore on this problem, so if I get stuck again, I'll stop, rather than risking spending another 45 minutes getting nowhere. But the idea that I had was the observation. First of all, I tried again with a 3x3 board just to convince myself that it couldn't be done. And I find that I noticed a rather useful little fact, a little lemma that you might say, which is that I can get rid of those two and put one here. Then I can get rid of those two and put one here. And then I can get rid of those two and put one here. So what that tells me is if I've ever got two consecutive rows of 3 like that, I can just remove one of those rows of 3. So that doesn't quite enable me to to get anywhere with a 3x3, because if I say I remove this board, then my only remaining move is to go up from there to there, and then I've got two things that are a bit too far apart. However, it does enable me, so with this sort of composite move that I've now devised, supposing I take a 4x4 board, and so that row of 3 is next to that row of 3, so I can just get rid of it. That row of 3 is next to that row of 3, so I can get rid of it. That row of 3 is next to that row of 3, so I can get rid of it. And now I had some idea for doing this. Oh yes, that's right. So this row of 3 is next to this row of 3, so I can get rid of it. Now I can move this one over to the other side and get rid of those two. Now I can move this one to here, and then finally I can move that one to here, and I'm down to 1. So n equals 4, we can do it. So as I say, that was a major change in perception of the problem, because I was trying to think of a kind of proof that would prove that you can't do it for any n greater than or equal to 3. I now wonder, since I can't seem to do it for n equals 3, but I can do it for 2 and 4, whether the answer is that n has to be even. It may not be as simple as that, but it seems very much worth experimenting. So this I've not done. I'd already offline made the n equals 4 observation. Let me just see if I can hack out a n equals 6 so I will just do it by, at least to start with, by getting rid of bunches of 3. That's 1. Get rid of this bunch of 3. Get rid of this bunch of 3. And then maybe I don't want to get too sort of pointy up there, so I'll get rid of that one, and that one, and that one. Now I've got to be careful, because if I get rid of that one, and that one, and that one, I'm down to a 3x3 board, which I know I can't do. So actually, I feel I've sort of been putting pressure on myself to do exactly that. So let's see if I can just reduce it to a 4x4 board somehow. Just quickly check, 6 squared minus 4 squared is not a multiple of 3, so I'm not going to be able to get it to a 4x4 board just by removing groups of 3 at a time, but I could at least have a go at getting part of the way there. So if I get rid of those 3 and those 3, and those 3 and those 3, now could I, if I got rid of those 3 and those 3, could I somehow get myself down to a 4x4 board? So maybe that one could go up to here, enabling me to get this one out of the way. I don't think this is working, but we'll just have to give it a little try. Those two down to here. That one down to here. So I haven't got a 4x4 board, I've got something, but is it something that I might have been on the way towards having, if I'd been doing the 4x4 approach? It doesn't look terribly like it, unfortunately. So I'm still not convinced that I can't do it. But before going any further, let's just see if there's any other number that I can. 1, 2, 3, 4, 5, 6, 7. I just want to see if there's anything else that I can do in a nice way. So I can charge down here with 3s. Oh no, maybe not. I say maybe not, but I think I can get to a 4x4 here. So I'll get rid of. Oh, sorry, my phone is ringing. Okay, so I've got a bit of silence to edit out of this video. But what I was noticing was that I can actually reduce the 7x7 to a 4x4 with no trouble at all. I just get rid of. I'm not going to cross this out actually because I may want to make a bigger diagram, but I get rid of those 3, those 3, those 3, those 3. Then I get rid of those 3, those 3, those 3, and those 3. Then I get rid of those 3, those 3, and those 3, and now I'm down to a 4x4. So I can do n equals 7, and therefore I can do, I think by precisely the same argument, I can do n equals 10, n equals 13, etc. And now because I could do, actually can I argue that n equals 4 reduces to n equals 1? That would be sort of nice by the same kind of technique, but I don't think I can quite. If I do 1, 2, no, if I remove 1, then I remove 1, and 1, 2. Yes, the reduction from n equals 4 to n equals 1 is not so simple as the reduction from n equals 7, 10, or 30. I can subtract 3 as long as I'm big enough. But if I can subtract 3, actually, can I get down to n equals 2 from 5? So this may turn out to be difficult. I might remove 1, 2. Let's try that. And then 1, 2. And then 1, 2. But I haven't quite got down to. And that's actually sort of, if I could get to one thing from here, then I would be able to do so from a 3x3 because I can get, oh no, sorry, I'm talking nonsense. So there might be a chance here. I don't see a way of doing it other than just sort of guessing. So let's have a. This doesn't look nice. 5 then looks still difficult. I'm going to guess that I can't do 5 still. 6 I couldn't see how to do. But 2 I could do. So one potential hypothesis is that I can do n equals 1 mod 3, and just by a fluke I can do n equals 2. But because there seems to be this ability to subtract mod 3. Mod 3 is significant in some way. I think I ought to try a bit harder with 5 before giving up on it. So what if I get rid of those two lots of 3 and I'm finding myself trying to do exactly the same as what I did before, which doesn't seem sensible. I could maybe get rid of one of these, and then I can move this slot over to here, just by hopping all those 3 over these ones. Is that going to be any good? Then I can produce a nice little shape, but it doesn't look a very promising shape. Perhaps if I do a couple of things like that. Got some things sort of dangerously spread out in some way. Oh yeah, so I can get this nice shape. I'm just going to do it because it looks nice, but I don't think it's very good from the point of view of the game. Because now I've got to go way out here. And I'm never going to reach that again. So that wasn't clever. So I really can do 2. If I can do 2, why can't I do 5? 3. It's because okay, one other idea. Maybe I've done this already, but I remove those ones, I remove those ones, as I have done this already. So I could remove that. But now I've got too long and thin a rectangle. That always seems to be bad, which could be part of a useful invariant based idea. Let's try something. I haven't quite convinced myself that I can't do this. So let's move that to here, then that to here. I better not move that to here because then I'm in, okay, this is not a good situation to be in. So, I might approve. I just want to see if I can think of any kind of mod 3-ish approach that will tell me that I can't get rid of all but one of these. So is there a mod 3? What if I look at the sum of all the coordinates mod 3, something like that? That doesn't look terribly promising because although here I'm going to have the sum of all the x coordinates being 0 mod 3 because I've got sort of 0, 1 and 2 in some order, the same with the y's. So if I were to add up all the vectors mod 3, I'll get 0, 0. But on the other hand, at the very end I might have 0, 0 as well, so And also, is it an invariant? Let's just check that. I think it might be actually, because if I've got 1 and 2, then I replace it by 0. And if I've got 2 and 0, oh dear, it's not an invariant. I don't replace it by 1. That's weird. So does anything happen mod 3 that's worth thinking about? If I start with a 0 here and I have a 1 here, I want it to be invariant, so I'll have to have a 1 here. And then I'll have to have, if I want it to be an invariant, I'll have to have a 2. But if I go back in the other direction, 1 plus 2 does not equal 1. So I'm in a sort of position that I've been in before, where with solitaire it's difficult to come up with an invariant that isn't forced to be trivial. So what I've just proved is if you've got a function from, supposing I have a and b, so just looking along a line, supposing it has to satisfy that that this must be a plus b, but it also has to be in the other direction, so that would tell us that a has to equal a plus 2b always, and that doesn't exactly help, because that means that 2b is 0, so if we've got a mod 3 invariant, then that will tell us that b has to be 0, and so in other words the invariant is going to have to be 0 absolutely everywhere. And I could think a bit about parity, I suppose, but if we just add up the parities, then, but that doesn't seem as though it's going to work either, because if I have, say, an odd and an even, and I replace it by an odd, that's fine, but I've got an even and an odd, and I replace it by an even. Now wait a minute, let's just try. If I have 0 and then 1, that's going to have to be a 1, but 1 and 1 does get replaced by 0, and then 1 and 1 has to be replaced by 0, and that actually works. So this one has to be 0 again, I think. No, it doesn't. This is looking mod 3-ish. I was looking at parity, but a mod 3 consideration has dropped out, which is that these are Fibonacci numbers mod 2, so it goes even, odd, odd, even, odd, odd, and they're because it's a palindromic infinite sequence, so to speak, then their Fibonacci numbers get mod 2 in the opposite direction as well. So I think I might have accidentally hit on a really good invariant. So what is the invariant? It's looking like this: 0, 1, 1, 0, 1, 1, 0, 1, 1, and then 0, 1, 1, 0, 1. It's got to be the same in all the columns. So here I'm going to have entirely zeros, I think. And then some ones back here again. I don't know whether I was absolutely forced to. I could have had a 1 here, for example. Then I would have had to have a... Yeah, no, I think I couldn't. So I'm fairly convinced that if anything's going to work along these lines, it's going to be this. All right, let's just see whether if I start with a square and sum up the parities of 4 things, I could end up with yes, no, the difficulty here is going to be I'll end up with one thing, but what's to say that it wouldn't be in a place where that will not be distinguished by this invariant. So for example, is this going to work to show that I can't do a 3 by 3? Supposing I start my 3 by 3 in, let's say, those places. Then the parities add up to 0. And if I end up with one thing, I could end up with it over here in principle, in which case the parities would still add up to 0 at the end of the process. So unless I can find an argument that says that at the end I will not that I'll have to involve a square that isn't one of these. So actually, what are these? These are just coordinates, let's say, where one of the coordinates is a multiple of 3. So what I'm actually looking at is parity of number of coordinates. Well, not quite. How can I define this? I mean, I could actually just look at the x-coordinate and the y-coordinates separately. So parity of number of x-coordinates that aren't multiples of 3. That's going to remain constant. Or is it? Because in the y direction, if I have a hop over, I'll lose a piece. And so the number of x coordinates will go down by 1. So it's actually not quite clear what is remaining invariant here, which is interesting. Yet this picture seemed to force itself on me, but I can't now see what to do with it. So if what am I adding up? I think I'm still adding up all these numbers. Oh yes, so when I add up these numbers, that is an invariant. When I add up the number of ones that are covered by the chips and take the parity, that will be an invariant. But I would like to have an argument that says, so when I had 3, if I got rid of a row of 3, that's going to remove, it's always going to remove two of these things. Is this going to enable me to prove anything at all? Like if I've just got a row of 3, I've got 3 things in a row, what goes wrong when I do a move? So say I initially had 1, 1, 0, then after that I'll have 1 and 1. That's got the same parity of covered ones. And but at the very last stage, this is more interesting. Or is it? If I want to end up with a parity of 0, when I've got one thing left, that one thing left has got to be a 0. So I'm either going to have 2 zeros, and this 0 hops over this 0 and gives me this 0, or I'm going to have 2 1s. This 1 will hop over this 1 and give me a 0. But that still doesn't seem particularly problematic. So I'm not stopping quite yet, just because this still feels fairly promising. But so when I had a 2 by 2, I do end up with 2 consecutive zeros. This hops over here, this hops over here. I got 2 consecutive zeros, and then I just get 1 0 at the end. And yet somehow if I have these extra zeros, then I can still get rid of this, and then I've got a 0 up here and some zeros down here, and it's not very clear what I've gained, but I suppose I could say that I don't just have this invariant, but I've got the same invariant however I shift this pattern here. That's sort of a bit, what do I mean by that? That's actually potentially interesting. So let's suppose I've got some method for dealing with a 3 by 3. Then at the end I'm going to have a piece on some square. Now let me decide what my invariant is only after doing that procedure. So I observe that however I shift it, I'm always going to cover a 3 by 3 with an even, that's always going to contain an even number of 1s. So there's one possibility like that. There's one that contains those ones, and there's also one where it contains 4 1s in the corner. So however I shift it contains an even number of 1s, but the square that I ended up in, I could shift it in such a way that it's a 1, in which case I will have had an invariant that started with an even number of 1s and ended with an odd number of 1s, and that will be a contradiction. So I think I've just found a really nice proof that you can't do 3. Now what I hope I'll find now is that if I take a 4 by 4, that's not going to work, because I can decide whether I have an even or an odd number of 1s. So I can certainly get an even number of 1s if I do it like this. But if I do it like this, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, so I get an odd number. So the proof that you can't do 3 by 3 fails for 4 by 4. What about 5 by 5? Do you always have an even number for 5 by 5? Well, you certainly do for this obvious 5 by 5. What about if I shift it down by 1? Then I'll drop by 4 and pick up a row of zeros, who cares? And now, alas, if I then shift by 1 in this direction, 1, 1, 1, I get down to an odd number of 1s. So 5 by 5, I still don't know. But actually that ties in with the fact that I was not able to reduce 5 by 5 to 2 by 2. So I'm beginning to suspect I will be able to do 5 by 5. 6 by 6, I can 1, 2, 3, 4, 5, 6. I can certainly get the obvious thing would be 4 plus 4 plus 4 plus 4, which is even. But I think I can probably get an odd one as well. So 1, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's even as well. Oh, wait a minute. 6 by 6, I think, is always going to be even because each 3 by 3 that it was made out of was always even. So 6 by 6, the proof that worked for 3 by 3, will also work. So you can't do 6 by 6. So 3 divides n, you can't do. And otherwise, I suspect you can do. We know that n congruent to 1 mod 3, you can do. And 5 by 5, I don't see yet how to reduce it to 2 by 2, but 8 by 8, I think we can reduce to 5 by 5 by the method that I had before. So we say we have, we draw a kind of 5 by 5 grid like that with a 3 by 3 going around. Then the technique would be get rid of all those, then get rid of all those until you end up with just a 3 by 3, and then get rid of that 3 by 3, and you're down to 5 by 5. So I will be done if I can just find some way of dealing with a wretched 5 by 5. And the problem will be much harder than I think if I can't do 5 by 5. So let us have one more attempt at 5 by 5, because if I can do 5 by 5, then I'll be able to do all others. And I'm still, even if I fail with this, I'm very happy now that I've managed to find an invariant, and slightly annoyed actually that I got sidetracked by the Conway invariant, so to speak, into writing a whole lot of nonsense earlier on today. So what can I possibly do that's just neater and cleverer that will get down to, let's get rid of just those 3 and maybe try and do something really symmetrical. So I'll get rid of those 3, and those 3. This probably is not going to work, but and maybe I'll hop over here. Now I'll hop over here. Now I'll hop to here. And here, this feels as if it's not going totally well. Up to here. That's in danger somewhere. But let's keep pressing on. If I move this one over there, then this one's going to be in serious danger. I'll do it anyway. The ones on the outside seem to be the ones that are problematic. So let's come in this way. Oh, so close. Let's have a look at that in the light of this picture here. I had a 5 by 5. Now I've ended up something which 5 by 5 could cover an odd number of things, because it could cover 3, 3, 3. So does that give me a clue actually about how I'm supposed to try to actually find the reduction. Should I be sort of in some way bearing in mind I suppose there's no chance of getting from a 5x5 to a 4x4. That would be crazy, but no, it really doesn't look as though there is. But let's just do that. This is sort of the other way of being symmetrical. I'll do that and that. Is that actually, maybe that'll help me to get down to a 2x2. And maybe it won't help me get down to a 2x2. I can get a 2x2 with a little tail on it, but that's not so nice. This is annoying. Get rid of those ones. Get rid of those ones. Hop this over to here. Hop this over to here. Put this one over to here. Put this one to here maybe. Yikes. Now I'm getting in increasing amounts of trouble. I've had it. So is there some other observation I can make that enables me to get rid of things? So I had a very useful lemma that told me that I can turn that into that. So could I just try and devise another lemma? For example, what if I've got 1, 2, 3, 4? What can I do with 1, 2, 3, 4? I know that 1, 2, 3, 4 I can convert into that because I put those two up there and up I go. Does that? The trouble with that is that it moves things out rather far, and it also requires a bit of space. I need but nevertheless, let's just try it. So those ones there I can put up here, and those ones there I can put up here. And now I'm going to have real trouble reaching those again. So that didn't seem like a very useful lemma. Is there anything else I can do here that I've not done that would show that 5x5 is not in fact possible? Somehow this seemed as though there was not a huge amount of else I could do. But might there conceivably be something after all. So, like, could I count the number of ones mod something else? It doesn't seem terribly promising, but what is the number of ones mod 5? For example, so I get, here I get 4 squared, which is 16. That's not, which is 1 mod 5. Whereas if I put it here, I get 3 squared, which is 9, which is minus 1 mod 5. Can I get anything other than 1 and minus 1? One, two, three, doesn't look very like it. Wait a minute, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nope, I can get 2, and I can get probably minus 2 somehow. But it's not even invariant, that's the problem. When I move this one over to here, it goes down by 1. So looking at the number mod 5 doesn't look at all helpful. That's very annoying of the question to I mean, annoying of the world of mathematics. It seems as though 5 you can't do, and yet the proof would have been so nice if you could do it. You see what I mean? It feels unlikely somehow that I've managed to find a proof that you can always do it when n is 1 mod 3. You can never do it when n is 0 mod 3. And that somehow, and that you can reduce by 3 as long as you're at least as big as 6. And yet somehow still not be able to get the 5. I suppose I could try just getting 8 down. So let me just try that. Can I get 8 down to 2? And I know that I should try to avoid getting it down to 5, because then I'll be... But I'm actually going to have a similar sort of problem, I think, because getting down to 2 is a bit troublesome, because especially if you're trying to get rid of groups of 3 one at a time, then you get this group of 3 intersecting with this group of 3. That is somehow what's causing all the trouble. 1, 2, 3, 4, 5, 6. And last one. But maybe if I just tried to get... Do I have a middle 2 by 2? Yeah, what if I tried to... So I could just go charging down here and then charging along here and charging along here and charging along here, except that I'm then left with a stray pair of things, a stray thing of 3. So that doesn't work. If I try to get this group of 2, then I can go down here and get here, so I can get it down. I can reduce, I can cut off that lot. I can cut it down to 5, but I'm trying to avoid doing that. So what alternative would there be, though? I could cut off all of this, but then I'm left with a really unpleasant bit sticking out. it's starting to feel as though I need to find another invariant, but what sort of invariant could there possibly be? Given that it has to be based on parity of something. If, that is, the invariant takes the form, I've lost, and not there, if the invariant takes the form, add up some coefficients, then we had this argument, I've lost where I wrote it, but if we've got an A and a B and a C, then we need A plus B to equal C if it's to be an invariant, and we need B plus C to equal A. So if I've got a weight of A on this square, a weight of B on this square, a weight of C on this square, and I'm summing the weights, and if I've got two chips there, the weight will be A plus B. And then when I do the move, the weight will be C. So A plus B will have to be equal C, and similarly B plus C will have to equal A. And so that tells us that B equals minus B, which only happens mod 2. Unless we perhaps take these things not to be numbers mod 2, but elements of some more general group, or of, say, an element of f2 to the n, or something like that. So does that get me anywhere? I will just try something. So if I had a 1, 1 here, and I think that's effectively what I've been doing, as a matter of fact. Then if I had a 1, 0, then the 1 next to the 1 is going to force a 0, and the 1 next to the 0 is going to force a 1. 1, 1, 0, and then 1. It'll go like that. 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1. And if I did the same thing in the other direction, 1, 1, 1, 0, 0, 1, and so on. But this looks suspiciously similar to what I was effectively doing before, where I said I could shift this invariant about as I wished. But maybe if I consider, maybe this does still help, maybe if I consider two shifts at once, I can argue that I can find so if I consider the shift, yeah, I have a feeling I might be able to do this. So if I consider this, and I also consider it shifted by 1 in, say, this direction by 1, so diagonally down by 1, I can find a position with my 5 by 5. Actually, what I want to ask is, can the 5 by 5 be have the same parity for both shifts? So if I go 1, 1, 1, so there I've got 1, 1, 1. I've got to get an odd one. If, say, I pick out that. Then if I shift it by 1, it turns into an even one. But I'm not 100% sure that if I went for the 3 by 4 thing, then it would be even. And then if I moved that down by 1, it turns into a 4 by 3. So it's still even. And that's slightly tragic, but I'm not giving up on this approach yet. What if I shift it by a knight's move? So if I shift it by a knight's move, then it's odd here, and then it turns into an even. Actually, which ones are even and which ones are odd? That's the simplest way of doing this. So if the top left-hand corner will be what marks out whether it's even or odd. So the top left-hand corner here, it starts off as odd. Now if I move it by 1, I'm adding 3, so it becomes even. Then I'm adding nothing, so it stays even. Then I'm adding an odd, and then I'm adding an odd, and then I'm adding an even, and so on. And similarly, if I move down, it's going to do this. And if I move diagonally by 1, it becomes even. That's the top left-hand corner. And here I've got 4 things in it. So however I move it, I'm going to have a multiple of 4. So that entire row is going to be even. This one here is an odd. And when I move it by 1, I will lose an odd. Oh wait, it's not odd. No. Oh, it's up here. No, it's not. It's down here. So it wasn't odd. It was 1, 2, 3, 4. That was even. And then when I moved it by 1, it became odd. And when I moved it by 1 again, it lost 1 and gained 1, so it remained odd. And then when I moved it by 1, it became even. Odd. This is annoyingly difficult to calculate, so even, it was even. Oh, I think I made a mistake here. So this one here has an odd number. What about this one here? That has an odd number as well. So I think this is going to do this. And what I'm trying to find, and I think I'm failing actually, is some move that will always take me from odd to even. But I think I can't do that because it's periodic with period 3. And so there's not a sort of nice match-up between the odds and the evens. Oh, but I don't actually mind that. I want something that I want it to be such that I want to move such that you never have both of them being odd. Perhaps that's enough. I think that is enough. Can I find a move that never preserves an odd? So the only way of getting odd is, I think, for the left-hand corner, let's say that, yeah, bottom left-hand corner, maybe not quite the only move. So let's have a look at the 9 possibilities for the top left-hand corner actually. So here are 9, it's periodic like that. So if that one, so that's all I need to think about. And I've thought about it here. But what I've written doesn't look as though it makes much sense. So let's just say what it is. Odd, because it's 1, 1, 1, 1, 1, 1, 1, 1, 1. And then even. And then odd. And then by symmetry it must be odd, even, odd. And I must check whether this one is really even. Yes, it is even. And let's get rid of all this. So the ones that I haven't really carefully checked, I've just crossed out. So this one here is 1, 2, 3, 4, 5, 2, 3, 4. So that's 3 times 4, so that's an even one. That must be even one by symmetry. This is the last one to try, and that looks like a 3 by 3. I mean, it's 3 ones in each, in 3 rows, so that's a 1. So now let's just quickly put a couple more of those in. Now, is there some move that will never involve 2 odds? Well, it looks as though if I just, if I shift it horizontally by 1, I can have 2 odds. But if I shift it diagonally by, if I shift it, we can think of this as a square that's repeated over and over again. And unfortunately, the difference set of a square looks like being everything. Except is that, yes it is. Because if I do a knight's move, I've got odd, odd. Maybe the evens are harder to get. So can I have something where there will always be an odd? At least one odd if I take this difference. So here I've got 2 evens in a row. Here I've got 2 evens in a row. If I do a knight's move, can I get from an even to an even? Yes, I can. So the different set of the evens appears to be everything as well, which is very distressing. And yeah, you can see that it clearly is, because you can get everything with 0 in one coordinate and everything with 0 in the other coordinate, and obviously the difference between 2 of those can be anything you want. So it seems to be very hard, unless I can think about shifting it 3 times. There's some pattern. I've just thought of something. So we have 4 things here where we get odd, but up here this is strange. The sort of pattern here was the same as the pattern here. Is that good news or is that bad news? That seems to be very bad news. Because what I was hoping to do was to say that the final position I can sort of arrange that I got, for example, I've got, when I do the shifts, I get it to be odd for some of the shifts and even for some of the shifts, and the way they're distributed looks like this. But the initial position with a 5 by 5, I was hoping was going to be different, but it actually seems to be exactly the same. That I've again got 1 by 1, I mean 2 by 2 squares of 1s separated by a distance of 1. So it really is, every invariant that I'm finding that will try to show that you can't do 5 by 5 is begging me to show that you actually can do 5 by 5. I've got to go in a moment, so I'm just going to have one more try at just finding a nice way of doing 5 by 5. How can I do this in a... I just want to do something beautiful in some way. So let's do something a little bit different from what I've been trying up to now. I'll just move that piece out there. Now I'm going to try and get everything over to here, so I'm just going to do pure guesswork really. That to here. Now that can go to here. Now that can go to here. That can go to here. I'll pull this one back to here so that that can go over to here, and that can go over to here. It's not too bad, but I'm not feeling very optimistic. Now I'm going to do the 2x2 little lemma to move that up to here. Perhaps I could get rid of that bottom 3 there, but that might be a little bit dangerous. So over here I'm a little bit worried. What am I going to do about it? Get this out of the way first, I think. That's what I'll do. I'll put that up to there so that that can come down to here. Then I can just bring that one that was far out a bit closer into the fold. Still some serious anxiety going on. This is really not looking good. This is going to get left far behind. I've absolutely had it. I could go back to the 3-ish approach. Just get rid of that and rid of that. See if there's anything else I can do. Now, I'm not going to try and get rid of those ones down here, because that I know leads to trouble. Is there any slight different thing I could think about perhaps doing? I could sort of do something weird like getting rid of this. Well, that's sort of... I could bring those two down. Okay, I know this, I've failed with this before, but let's just try once more. No go. What is the idea that I'm missing? So with that 1, 2, 3, 4, 5, I can place it. I think it'll still have the property that I can, when I place it here, I can make it either even or odd. So 1, 2, 3, 4, 5 is odd, but 1, 2, 3, 4, 5 is even. 1, 2, 3, 4, 5 is odd, odd. It's going to be just the same idea that whether or not it's even or odd will depend on it will look like this pattern here. That's just really strange. That is my last attempt before I unfortunately have to stop. I wasn't really intending to make this a long one. But let's just put those out here for a moment. And get rid of those. Get rid of a bit of this stuff. I think I'm going to get back to a position I've been in many, many times. If I put this here, then I've got a 3x3 with two things removed from it. If I move those two over to here, I can get back to my L shape thing, which I know doesn't help. And could it be that the arrangement that you need just before the last one is problematic? If I just have two things like that, what will their pattern look like? So it'll be even, 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 odd, even, odd, odd, even, odd, odd, even. It'll be, yet again, it will be the 2x2 squares of ones pattern, so it will not help. I think actually in retrospect that was obvious. So this pattern is somehow preserved. So it's only if you don't have the pattern to start with that you've got any chance. And so what's annoying is that the pattern occurs at the end as well. And it just happens if you start with something that's a multiple of 3, you always have an even parity, so you don't get this pattern. Okay, well, I was rather pleased with the partial progress, but it's tantalizing not to be able to finish it off. I certainly wasn't expecting to waste half my day on this problem. But there we go.